do one slide, right? Yeah. But guys, I would propose to you that all of the time that we spent making sense of this was time very, very well spent. Because guys, you now have a foundational basis for what is going on with equilibrium, at equilibrium, how we get to equilibrium, what is equal at equilibrium, where the equilibrium ratios come from, the rate constant ratios, right? Because you have an understanding of equilibrium that's really robust. So guys, we're not going to look at homework, but are there things that I don't know if you were mulling this over in your brain over the last couple days. Is there anything here you want to dig into a little more deeply before we get going? Feeling okay? No burning unanswered questions? Yeah?
Was the thing we were talking about, like the blue water going back and forth?
Yes.
Okay.
Yeah. Yeah. It was really bad during COVID because and you probably don't remember, but we do general chemistry, we do equilibrium in late April and May, hot in the middle of COVID 2020, right? So we had to figure out how to take that thing and send it home over Zoom. And we actually found a YouTube video where a guy had two big Tupperware containers and two different cups, and he was scooping out of one and scooping out of the other. The problem was it didn't represent the idea that the rate was changing, always slowing down, because his cups, one was bigger than the other, but his cups always had the same amount of stuff in it. It took us a while to recover the next year in AP, but we sorted it out. But yeah, it's really the best analogy. But yes, it was the blue stuff. Guys, any other thoughts or questions or things you all want to talk about? Okay, then gang, this is what we're going to do today. We are going to build on these foundational ideas, and I'm going to try to not get the blue juice out, simply because I think we have a strong enough memory and connection with it that hopefully we can refer to it without having to see it. But guys, with that said, and with everything we talked about last time, my hope is that the next couple ideas, you can just sort of nod your head and go, yes, that makes sense. If you can't, you need to ask. Then guys, once we're done with these additional conceptual things, we're going to mathematize this a little bit, but we did it last year in Gen Chem. The Kc values, products divided by reactants, will bring us back to that. And then guys, we're going to talk about, these are our big idea, our new ideas today, homo and heterogeneous equilibria and Q values. We need to save ourselves some time to talk about those because they are big ideas that are going to be foundational. Heterogeneous equilibria is huge for the next unit, and Q values, ready for this, is huge for the last unit, which is the next to next unit, which is electrochem. So guys, the last two things we're going to do today are really foundational to what we're doing for the rest of the year. So guys, with that said, can we just say yes? So guys, and we looked at this in the book, but let's really sort of bring it together. Guys, when we reach this condition of equilibrium, the amount of stuff that's moving forward is moving backward at the same rate. When that happens, two things happen. The rates become equal, and the concentrations become constant. Guys, if that is really not an understanding that you own, you need to be proactive and ask questions. But guys, this is foundational. At equilibrium, the forward and reverse rates become equal. Therefore, the reaction is always doing and undoing itself. And as a result, the amounts, the concentrations, become constant. Can we just agree to that and move on? I'm not seeing nodding, which is fine, but if the answer is no, I need to know. You okay? Okay. Then guys, what about this? We can come at equilibrium from any direction. So you guys are going to look at the screen and not think through this with me if I leave that up on the screen. But guys, can you picture the tubes? And we're doing the flippy thing, right? And eventually the big tube was at 70, and then the bottom tube was at 30, right? And then we came along and we said, hey, what happens if we dump in some, can you picture this, or should I get the tubes? Am I okay? So we dumped in some reactant and we kept going. And we said that because there's now more reactant, that accelerates the forward reaction. So some of that reactant is now turning into product. So the amount of reactant goes down, the amount of product goes up. And eventually we end up at the same 7-to-3 ratio. It's just not 70-to-30 because we got more stuff. Is that okay? And guys, then we said, if we come along and we take away some reactant, now the forward, thank you. Now, oh, here, I got so much stuff. Yeah, appreciate you. So guys, then the idea is that if we take away all the reactant, the forward reaction rate initially is 0, and then the reverse reaction starts replacing it, but it always goes back to 7-to-3. That's what this is about. Guys, the idea is this. And guys, I would encourage you to write this down. This, let me tell you what, this is the only named reaction that you need to know in AP chemistry. It's called the Haber process. Write that down. It's called the Haber process. Haber. Yeah, this is some would argue that this is the most important reaction on Earth. Because the problem is that, well, right, and then guys, right here, let me do this. Then write this down too. Just a moment. Come on. There we go. So guys, the balanced equation for this. The balanced equation for this is, Andy, you can just leave that and go, is this N2 plus 3H2, 2NH3. Guys, you have to know this reaction. It's called the Haber process. We'll talk about the problems, then we'll talk about the so whats. So guys, what are we talking about in this unit? What's the big idea? Equilibrium. What's wrong with the reaction? We need a double-headed arrow. I find it interesting that I lifted this straight out of our AP book and it's wrong. But Joni, you're absolutely right. Guys, if you're interested in knowing the chemistry behind this, just really, really quickly, you know that our atmosphere is made of 70% nitrogen, right? Plants need nitrogen in order to grow. The problem is this. This nitrogen is triple bonded together, and I was about to say there isn't a plant on the planet that can break this apart. That's actually not true. We'll talk in a second. But guys, plants don't need nitrogen molecules. They need nitrogen atoms in order to grow. And so guys, there's a class of plant that can actually break that triple bond. They're called nitrogen fixers. Did you learn about this in biology? So legumes, beans, things like that, they are nitrogen fixers. They have the amazing ability to grab N2 out of the air, break the nitrogens apart, and shove them in the ground. So it used to be when we were farming, what we would do is we would actually, every couple of years, farmers would plant beans. And the beans would replenish the nitrogen in the ground. Well, guys, it turns out that we needed a much better way to do that during World War II because all of the men were overseas and there was no one left to farm. The problem is that this reaction, the equilibrium lies hugely to the left. And because the equilibrium lies hugely to the left, it was really, really hard to take nitrogen and hydrogen and figure out how to turn that into NH3, which is ammonia. Guys, this is our source of nitrogen. Plants can rip the hydrogens off of ammonia and get to the nitrogen. The problem was it was hard to get this reaction to go. Now we can at an industrial scale because of some dude named Haber, and people would argue that he is actually the reason we have 9 billion people on the planet right now, or whatever the number is. Guys, the reason that our planet can at some level support this number of people is because we have a source of nitrogen that wouldn't exist otherwise, so we can farm on an industrial level. So there's your history lesson. Yeah.
So the equilibrium will usually are like on the reactant side.
Correct.
The nitrogen. Yeah, because the nitrogen bond is way stronger than the nitrogen.
The problem with your thinking is that you don't know the mechanism,
Okay.
right? You can't talk about why until you know the mechanism. And again, as we learned in the last unit, this isn't a mechanism. So in order to understand why the equilibrium lies to the left, you need the mechanism. I will tell you this. In order to get the equilibrium to shift to the right, you got to heat this up and pressurize this to the point where it wants to explode. And it has exploded and killed a lot of people in the process. But in order, and that's what Haber did. He figured out an industrial way to heat and squeeze this to the point that it favors products. And that was the genius of what he did. Okay, so guys, beside the point. You do need to know the Haber process. But guys, this is the deal. So here, so looking at these graphs, let me zoom into them with you, and then let's talk. So guys, the idea is this. If you start this reaction with a fair bit of H2 and a fair bit of N2 and no NH3, when this comes to equilibrium, these are the concentration ratios. Then guys, over here, if you start with 0 nitrogen and hydrogen and you start with a lot of NH3, you end up at the same equilibrium, just like we did with the tubes. If you start with a lot of reactant and no product, equilibrium. If you start with all product and no reactant, same equilibrium. There's a name for that. And guys, it's all reflective of Le Chatelier's principle, but we're going to do that later. So guys, are you okay on these ideas? Yeah?
If you like always have this reaction to work products,
Yeah.
the product's concentration on this again, please?
I don't know. That's interesting, Claire. Not to be weird, but frankly, the answer relative to this class doesn't matter. With that said, that's interesting. Would they have to find? I mean, it's kind of like the old idea that if you take hot water and cold water and mix them together, it can't get hotter and it can't get colder, right? It's going to be in the middle. But I don't want to say yes. And the reason that I don't want to say yes is that many times, and we're about to talk about this, these relationships are seldom arithmetic. They tend to be exponential forms, in which case I think the answer could be no. Yeah, but that's a fascinating question. I've never thought about that. But I think the safe bet is no, and I think mathematically we're about to see why. Okay. All right, so guys, are we good on this? Okay, then, we're going to click through this super fast. No, we're not, because I don't have a clicker. Now we're going to click through it super fast. Look, math. Don't write it down. Because, guys, you learned this last year. Yes, John, you learned this last year, and I know you remember it fondly. Guys, we have what are called KC expressions. KC expressions are always product divided by reactant ratios. And the idea here, guys, is that if we have a balanced equation where A and B are forming C and D, And then we have the coefficients from the balanced equations. Guys, in getting from this to this, it's always the right side on the top. It's always products on top. It's always reactants on the bottom. And then, guys, sorry, these aren't superscripted all the way, but the coefficients from the balanced equations become exponents. And then the plus signs become multiplication. And this is what is called the KC expression. Do you remember that from last year? Is that okay? You good? John, fundamentally, that's the deal. This is like our 70-30 ratio, where we had 70 products and 30 reactants. That is this. But the idea is that when we have more complicated reactions, products on top, reactants on the bottom, the brackets are molarities, and then the exponents are the coefficients from the balanced equation. Is that okay? Again, Clara, leading us back to the idea that I don't think your hypothesis is universally true because of the exponents. Yeah. Were you going to go somewhere, Ivan? Hold on. Where's my minus sign? Yeah, it was a scribble. Don't confuse scribbles with information. You guys okay on that idea? Okay, so guys, what about this? And we're going to come to this in a minute, but we should talk about this right now. So we understand that this is products divided by reactants. So guys, what does this mean? If Kc is greater than 1, what does that tell you about the equilibrium? It means there's more products. Does that make sense? Guys, what if the Kc is less than 1? Then the equilibrium favors. Does that make sense? That we're dividing. So in order to be less than 1, remember this is products divided by reactants. So to make this fraction have a value less than 1, this has got to be the larger number, meaning there's more reactant. Does that make sense? Now guys, in this class, let's put this in context. What does greater than 1 look like? It starts at about 10,000 and goes up to billions. Okay, what does smaller than 1 look like? It starts at about 0.001, 10 to the negative third, and it goes down to like 10 to the negative eighth or ninth. So guys, we really don't hover around 0 very much. Our Kc values are going to be huge or they're going to be really small. There's not typically a lot of gray area in between. What about this? What if Kc is negative? It can't be because there's no such thing as negative molarities. Huh? All right. So guys, Kc, you good? Questions on that? What's that? Oh no, nope, that's pretty hard and fast. But guess what, guys? We can not only write Kc values for concentration, we can also write them for gas pressures. Hooray! So guys, just same idea, different context. If you're looking at pressures in gas mixtures, instead of writing Kcs, we can write Kps, where the P is the partial pressure of each of these gases. So guys, how does this work? Are you guys writing or can you think about this with me? Just remember there are things called Kps, and then the idea is the information you plug into the equation are partial pressures, atmospheres, rather than molarities. Does that make sense? Can we talk about this so you understand it? So guys, what is it that determines, let's imagine that we've got a Kc or a Kp, and this is products divided by reactants, but let's go back to Kc first because we're more familiar. What is it fundamentally that determines the product to reactant ratio? We did the math last time. Clara, we derived an equation. It was so good. I would really, but it would have been better with you. So guys, what is it that determines the value of this ratio? The ratio of what? K values, right? little k forward divided by little k reverse. Yes? Okay. Now, how does that then tie in to concentration? Well, the idea is if we know the K forward and if we know the concentration, those come together to give us a rate. Does that make sense? So we've got our K values, rate constants. We've got concentrations, that gives us rate. But what about this, y'all? How does pressure lead us to rate? And the answer is, if you've got a container of a fixed size, and if you pump more moles in there, what happens to the pressure? Goes up. So guys, in that sense, pressure is like a molarity, because the size of the container is fixed, and as you pump more gas in there, you have a higher concentration of the gas, which then leads you to a rate, which then leads you to this expression. Yeah.
So essentially, but you just never solve for
You never solve for molarity, yeah. But what you're going to see in the homework is this. The homework authors get really creative with this, and what they do, you'll see this in homework today. They say, assume that you have a 1 liter vessel, and there is one mole of gas in that 1 liter vessel. Well, we can go PivNert, and we can figure out the pressure, right? So that would give us pressure and give us this. What they do is this. They cut corners and they say this is moles, this is liters. Molarity is moles divided by liters. And they make a fake molarity that isn't the concentration of something dissolved in water. It's the concentration of moles inside a 1 liter container. The logic works because T and V are constant, and so there's a direct relationship between moles and pressure. We established that earlier. But you're going to see in the homework, you're like, wait, this seems like a gas pressure problem, and yet they solve it with Kc because they're creating a fake molarity. But guys, fundamentally, you're good. Kc expressions for concentrations, Kp expressions for gases, they work the same. All right. Guys, now it's time to engage and start doing business. Oh, by the way, I should mention this. Guys, back in the good old days of AP, we used to have to teach this. There is a way to convert between Kp and Kc. That equation is no longer on the equation sheet, but I left the question in the homework, not because you need to know it, but because I wanted you to see it, so that when you see this in college, it'll be a little familiar. Okay? All right. So, with that said, here we go. So, guys, can we all agree to this? If Kc is bigger than 1, if it's large, if it's huge, remembering that Kc or any K value is products divided by reactants. If the number's big, we got more product and the equilibrium lies to the right. If Kc is small, never negative, but small, we've got more reactant, so the equilibrium favors reactants and it lies to the left. You good on that? Okay. See how we're doing? All right, then guys, what about this? Hold on, this is going to freak out. You okay? Were you playing the role of Mila? Okay. Guys, what about this? What if we switch the reaction around? So guys, imagine that we've got products. Imagine that we've got reactants yields products, and our K, let's do this. Let's give them names. So imagine that we've got X leading to Y, and our Kc then is, I'm going to not put the brackets because that's, anyway, you get the idea. Products divided by reactants. What if we flip them around? What if we call the reactants the products and the products the reactants, which really is not that big of a stretch because they're at equilibrium anyway. So guys, if we flip the products and the reactants, what happens to the value of Kc? Flips over. So would it be okay to say this? It's inverse Kc. You're going to see that in the homework as well. All right, you guys good? Let's keep going. Woo! We are cruising. What's up? Ah, I like it. Guys, this you need to write down. This is, in the words of our dear friend, Mr. Ellingford, important. Because Mr. Ellingford overpronounces pretty much every word in the English language. Even his own name, Ellingford. It's Ellingford. Yeah. Oh, yeah. Yeah. A couple of years ago, Ellingford's, I won't tell you, his actual first name got out. Brian's his middle name.
Wait, what's his actual name? It's gotta be
I can't tell.
Is it?
It is not Eugene. No. Oh, yeah, that's what Google's for, right? All right, guys, don't miss this. This seems easy until you find out it's going to screw you up. So, guys, not surprisingly, in homogeneous equilibria, all of the substances are in the same phase. An example of that would be the Haber process. What's the Haber process, you ask? You should know it. But then, guys, we've got heterogeneous equilibria. In this example, the substances are in different phases. Now, guys, there's something really important that you need to know about the distinction between these. But rather than tell you, I'm going to let you sort it out on your own. Guys, you understand that increasingly we are doing AP review. This was early September. Write the net ionic equation and then the Kc expression for the reaction between aqueous potassium iodide and aqueous lead-2 nitrate. Actually, you know what? Let's don't. Rather than net ionic, let's do complete molecular. Let's just keep it simple. So guys, write the complete molecular equation for the reaction between potassium iodide, yes, our favorite catalyst for the decomposition of hydrogen peroxide. And you guys can grab your solubility charts or what. So guys, complete molecular equation for Ki and lead-2 nitrate. Reactants, products, balance it, write the Kc expression, go. Some of you right now may also be reaching for your little running to-do list of stuff you need to remember. You got solubility rules, you got net ionic equations, although we're not asking you to do that. Okay, it's hot in here.
Yeah. For the first time in
So how do I tell Steve, our head custodian? Because for the last 2 weeks it's been, hey brother, send us some heat. We're dying up here.
You either get this colder or really hot.
Right.
Maybe Cracker Rice is really
Whose?
Mr. Rice. His room's always super cold.
So I have a question for you about that. You have Rice. If I were in Rice's room, they would have to lock me in a padded room after about a week or two. That weird low-level colored light in his room would send me over the edge. The one that's worse than that is Miss Gelfie's room. It's bad. But seriously, like, so do you walk into Rice's room and just go, huh? Because I would walk into Rice's room and I would go sideways. Like, yeah.
We usually have the lights off because Rice just don't let me watch movies. Sounds nice.
Is that right? Really? Huh.
It was like, I don't know.
So guys, let's do this. If you're done, you're wrong anyway. And if you're not done, we may as well save you the trouble. So guys, do this with me together, because you're about to see something interesting. Okay, so we've got Ki, and we've got lead. We've got lead 2 nitrate. How do I know that's lead 2? Because I know nitrate's -1 and there's 2 of them. Therefore, lead has got to be +2. Reviewing for the final. Then guys, we come over here. Potassium hooks up with the nitrate. Those are +1 and -1, and consequently we get this. And then the lead iodide, lead's +2, iodine's -1, so it's this. By the way, guys, just as a weird coincidence, this is the reaction that I want to do with you. When, you know how we said when somebody's done with the last trial, we were going to get together? This is what we're going to do. Let me explain to you the logic, and then we'll get into what we're talking about. But guys, remember the idea is that iodide is a spectator. So it goes in here, and then it comes back out. So the left-hand side of this is what you're doing in your burette. So the idea is that iodide goes into the reaction with the hydrogen peroxide, and then it comes back out. So what we're going to do is we are going to take the reaction solution in your flask when we're done, and we are going to add lead 2 nitrate. If there is iodide in that solution, it will precipitate. Because lead 2 iodide, remembering our solubility rules, all the halogens are soluble unless they're bonded with silver, lead 2, or mercury. So if in fact there is iodide in the products of your hydrogen peroxide decomposition, we are going to see this very vivid yellow lead 2 iodide precipitate. Get the idea? So what does that have to do with what we're doing now? Well, let's balance it. We need a 2 here, and we need a 2 here, and then we go Kc is equal to KNO3 squared PbI2, no exponent, and Ki squared, and then PbNO3. Is that all right? Okay. Kc expression, right? Okay. So guys, what numbers then satisfy this equation so that we can solve it? What numbers do we need to fill in the brackets? We need molarities. But now guys, this. We've already talked about this visually, and you're sort of imagining it happening in lab in an hour. But guys, let's talk. Does potassium iodide dissolve in water? You have a squirt bottle of it sitting next door. Does lead 2 nitrate dissolve in water? How do we know? All nitrates dissolve in water. Does potassium nitrate dissolve in water? Same reason. Does lead 2 iodide dissolve in water? It's our precipitate. It is a solid. You're going to see it in a minute. It's fancy bright yellow. So now, guys, in order for us to satisfy this Kc expression, we now have a really big problem. This dissolves in water. It'll have a molarity. This dissolves in water, it'll have a molarity. This dissolves in water, it'll have a molarity. This don't dissolve in water, and as a result, it ain't got a molarity. And the molarity is not 0. Instead, it's this. This does not belong in your Kc expression. Guys, again, tipping our hat, this is important. They're going to trip you up on this. They're going to have you write Kc expressions. And guys, and let's use the word, this is a heterogeneous equilibrium. Aqueous, 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 solid. Guys, when that is the case, anything that is a solid does not belong in your Kc expression because it doesn't have a molarity. It doesn't belong in your Kp expressions because it's not a gas. It doesn't have a pressure. Let me do one more thing. You okay on that idea? Another example. Sorry. That should just be H2. See the problem? Water's a liquid. It ain't got a pressure. We're not talking about water vapor. We are talking about liquid water decomposing into its gases. And guys, water is a liquid in this example. It is not a gas. Consequently, it doesn't have a pressure, it doesn't have a molarity, it doesn't go in Kc. So guys, here's the big idea. Excuse me, I'm hiccuping. When you do Kcs or Kps, you will never have pure solids or pure liquids in your Kcs or Kps because they ain't, bless you, they ain't got pressures and they ain't got molarities. You okay? Jared, where did you want to go with that? Yeah, and so are we okay? Okay, so guys, let's put a fine point on this. It's literally then this. When you write equilibrium expressions, you never include factors for pure solids or pure liquids. For now, we're going to leave it at this. The reason why is because solids and liquids do not have pressures and they don't have molarities. When you get into P-Chem your junior year, we'll let those professors try to explain to you the real reason they don't go there. But guys, when they struggle to explain it to you and your head's about to explode, you can just remember it's because they don't have pressures and they don't have molarities, and that'll get you through. But the actual, if you were to go to a P-Chem professor and say, I'm writing heterogeneous equilibria and I don't include solids because they don't have molarities, they'll kick you in the shin. It's not actually, the answer is we can't talk about it. I don't know that I could explain it. But guys, for us, this works. You guys okay? All right. So guys, again, not really the reason. But guys, do understand this. It does not mean that we cross them out of the balanced equation. They've got to be there to balance the equation. It just means they don't show up in the KCs. You guys good? One more, or let me do it. Is anyone not good? Better question. No, good question. So is there no Kp for the decomposition of water? And the answer is yes, there is. It just doesn't have a denominator. Yeah. Right. Then, yeah. With that, Shoot, you're going to get mad at me. We're going to do it anyway. Yeah. Oh, no, let's do the one you know. So silver chloride, right? I think you guys have made this precipitate about 11 million times, right? Most recently, it was the stuff that we collected in the filter paper that we used to trap the chloride out of our unknown salt. And we did the gravimetric analysis lab and we isolated the chloride and figured out the formula mass of the percent chloride. You know what I'm talking about? So guys, silver chloride doesn't dissolve in water, right? It actually does. Silver chloride actually is what we call slightly soluble. Very slightly. Guys, if you have, well, for example, you guys know that when we did this lab, right, we just added silver nitrate to it forever, right? And the silver chloride all precipitated to the bottom. A little bit of that silver chloride did dissolve. I'm trying to do the math in my head, but I think that the molarity of it is like 10 to the negative 7th molar. It's really low. So guys, we treat silver chloride as being non-soluble because for all intents and purposes, it doesn't dissolve. But in reality, it does dissolve a little bit. And we're going to talk about this in chapter 17. They're called slightly soluble salts. Elizabeth, why are we talking about this? And the reason is this. When we write the Kc for this expression, it looks like this. Yeah? But what shouldn't be there? This guy. This is the solid, right? This is solid AgCl. This is these ions dissolved in water. Does that make sense? So this is heterogeneous. Therefore, this shouldn't be there, and it goes away. Guys, what you're going to find out in chapter 17 is this. We no longer call this Kc. We call it KSP. S stands for solubility, and P stands for the mathematical term product. But guys, when we have a product of a calculation, what math have we done? Multiplication. That is this multiplication. So guys, when we look at slightly soluble salts, there is never a denominator because that's the solid in its undissolved form. And so what we end up with is just the concentrations of the ions, their solubilities multiplied together, and we call these solubility products. So there is an example of a place where we also lose a function, a part of the fraction, but you guys are going to see we do this a lot. You guys good? Okay. Guys, we've got one more thing to do. Bum, bum, bum. 8 minutes, we got this. Reaction quotients. If product implies multiplication, what do quotients imply? And those kind of look like fractions. So guess what we're going to do? We're going to talk about reaction fractions. Well played. So guys, here's the trick though. We already have, I've never called them this before. We already have reaction fractions. They're called Kc values, right? So guys, I'm not going to give you notes. I'm going to help you develop an understanding of what we're talking about. And guys, we are going to come back to our tube, 70 to 30, right? So guys, here's what we know. We know that Kc, I would encourage you to write this down, is products divided by reactants. Now let's talk about blue tubes. 7 divided by 3. That is a quotient. 2.3. Bigger than 1. What does that tell us about the equilibrium mixture if Kc is bigger than 1? More products, right? And guys, this can get a little muddled at times. If you ever get into the middle of this and you're not sure, shoot, I don't remember, big Kc, what does that mean? Just remember, guys, that it's always products divided by reactants. And if the value is bigger than 1, then that means the numerator is bigger and the numerator is products. Get the idea? Now this. What happens if we take a reaction like our tube thingy, and if we start messing around with it? We add reactant, we remove reactant, we add product, we remove product. Guys, what is this reaction always going to do? Come back to 7 to 3. Yes? Okay. This is what Q allows you to predict. Guys, and Q is the reaction quotient. The reaction quotient allows you to predict what direction the reaction is going to go to get back to equilibrium. The reaction quotient Q allows you to predict which direction the reaction is going to go to get back to equilibrium. So guys, let me show you an example. Let's say, let's do the easier math first. So guys, can you picture our tubes at 70-30? And guys, imagine that I come along and I dump in some product. So now, let's say this is 12 and 3. So now guys, can you picture that this means that I dumped in more product? So now this tube is bigger than it should be? Can you see that? Okay. So guys, then as we continue and we keep flipping, what's going to happen to the amount of product? It's going to go down, and the amount of reactant is going to go up until they come back to 7/3, right? So guys, here's what we know. This reaction is reactants in equilibrium with products. And now we've got too much product, yes? So if we've got too much product, the reaction is going to get rid of product, turning it into reactant. Does that make sense? So what direction does that shift the equilibrium? To the left. Now guys, this. What if we come along and go the other direction? What if I come along and, I don't know why 12, it's just in my head. Guys, what if we have now our reaction at equilibrium and I go and I dump in a bunch of reactant? As I continue to go, what's the amount of reactant going to do? Go down. The amount of product will go up. So now we're making more product, which shifts the equilibrium, drives the reaction to the right. Does that logic make sense? Is that okay? Okay, now let's do this. 12 divided by 3, thank you. 12 divided by 3 is 4. 7 divided by 3 is 2.3. So guys, when we talk about the situation on the left, Q is greater than Kc. This is important. Q is greater than Kc. So what is Q? Guys, this is Q. Q is Kc solved at non-equilibrium concentrations. Yeah? So guys, we know that this situation on the left is not at equilibrium because it's not 7/3 or 2.3. And because it's not 2.3, we know that this reaction wants to get back to 2.3. But guys, this number Q is bigger than Kc. That means we've got too much product, so this reaction is going to shift to the left to get rid of the extra product. Does that make sense? Now, guys, let's go over here. 7 divided by 12, we're going to call about 0.5. That's close enough. But now, guys, our Q is less than Kc. That means our denominator is too big. We've got too much reactant, so that reaction wants to get rid of the reactant, and therefore it's going to make more product. Does that make sense? Is that okay? So guys, let me bring this full circle for you. Tell me when you're ready for me to clear the slide. Is that okay if I do that? Okay, then this, guys. Going back to square one. This is going to take 1 minute. We have a reaction where reactant is turning into product. Our Kc value is products divided by reactants, or 7:3. What does that value, 7/3, tell us about the equilibrium? There's more product at equilibrium. Guys, that value Kc, and the way that we say it, we really, and again to your point, Clara, we're really careful with more. Thank you. We're really careful with more because these relationships can get complicated. So here's the way we say this. The value for Kc is greater than 1, therefore products is bigger, right? So here's what we say. We say Kc is bigger than 1, therefore the reaction favors products. The word that we use is favors. Is that okay? Then this. Again, this is 2.3. Now, guys, imagine that they come along and they tell you that this reaction at any given moment has a K of, a Q value of 5. So guys, remember, Q is Kc solved, not at equilibrium. So is Q too big or too small? Too big. That means our amount of product is too big. This then tells us the direction the reaction will proceed in getting back to equilibrium. So here's how we talk about it. Q is larger than Kc, therefore the reaction will proceed towards reactants, or you could say to the left, to get back to equilibrium. So guys, Kc tells us where the equilibrium lies. We use favors. Q tells us the direction the reaction will proceed to get back to equilibrium, and those are the words we use. To get back to equilibrium, this reaction will proceed because we've got too much product to the left to turn product into reactant. So Q is used predictively. Do you get the idea? Yo, yo, yo. And for those of us that love pretty pictures, the book talks about it like this. If Q is bigger than K, we've got too much product, so the reaction proceeds to the left. If Q is too small, we've got too much reactant, and so it proceeds to the right. When Q is K, it's at equilibrium. Look, pictures. Look, homework. Oh, yeah. All good things end with homework. So, guys, take a break.